Okay, now I will present our IoT project, Smart Plant Modeling System. We are the group three. We group member, we have 6. There is our leader Lin Zhenyu, and me, Tang Jinglang, and Anina Lin Sihong, Peggy Chua Pei, and Nathan Chua Haoyang.
Okay, this is our problem statement. The first, manual and rigid schedule reliance on human observation lead to inconsistent care and timing error. Environmental inaccuracy. Traditional method fail to adjust for dynamic change in temperature and humidity. Health risks. Underwatering lead to plant desiccation, that is, drying out. Overwatering. It will cause the root rot and significant water wastage. And the last, zero remote visibility. Caretakers have no way to monitor or react to plant needs when away from the site. Next. So we have 4 objectives. The first one is system development. Design a complete IoT ecosystem for smart monitoring and automated irrigation using ESP8266 and ThinkSpot. The second is sensor validation. Implement and evaluate the performance, accuracy, and reliability of THT11 to detect the temperature and humidity. The second is analog soil moisture to detect the water levels. And the third is PIR sensor to detect the motion. And the data visualization, collect and analyze a minimum of 500 data samples through a centralized ThinkSpot cloud dashboard. And the last is comparative analysis. Demonstrate the technical and resource-saving advantages of an IoT system over traditional manual plant care.
Okay, thank you, Tan Jinglang. Right now is methodology part and research design. First, you can see here is our simple prototype for utilize hardware prototyping and experimental methodology. Also, we have edge computing that develop a single node edge device for localizing testing. And the third one is need to control environment, evaluate, automate irrigation logic and real-time monitoring within an indoor setting. Also have iterative testing, allow for continuous refinement of sensor accuracy and telemetry stability. Okay, next. So this is our 4-layer system architecture. For the 4-layer is about utilizing the ESP8266 MCU built-in Wi-Fi capabilities. The process telemetry data is transmitted through the HTTP and POST protocol, open source ThinkSpot cloud platform. And also the third layer is the soil moisture drop below a predefined threshold. The microcontroller autonomously actuates 3.3 volt DC mini submersible pump. And also the second layer is the ESP8266 microcontroller act as the central edge device. It processes the raw analog and digital signal locally. And for the first layer is environmental data is continuously gathered by a DHT11 temperature and humidity sensor, an analog soil moisture sensor, and a PIR motion sensor. Okay, next. Yes.
Now I will present about the literature review. Internet of Things refers to a network of physical devices that can collect, exchange, and process data through the internet without requiring constant human interventions. An IoT system typically consists of sensor, communications network, processing unit, and cloud platform. Inaccurate IoT helps monitor environment conditions such as temperature, humidity, and soil moisture in real time, improve efficiency, and reduce manual works. Besides that, to the related work, several researchers have developed IoT system for smart accurate. Para and Disaka developed an IoT monitor system that improve accurate productivity and water management, but it requirement expensive infrastructure. Sono and Collagrates proposed a scalability IO framework. However, it was technical platform and difficult for beginner. Gonna integrates architects intelligence into smart framing, but the system require high computations resources and larger datasets. Vera Size demonstrated a simple IoT monitoring system using the Blink platforms, but it lacked advanced analysis and dashboards customizations. Next to the compresses of IoT platforms, we compare several IoT cloud platforms. While Blinks and Thinkispinks are easy to use, they offer limited visualizations and analysis. AWS IoT and Google Cloud IoT provide powerful features but are expensive and difficult for the beginner. Therefore, we select the Thinksports because it offers advanced dashboards, history data store, scalability, and low implementation costs. Next, I will pass to my partner.
So now I'll present about the firmware and local closed loop control logic. And here we can see the two coding. Here got the first of the initial of the coding, and the second we got next. And here we can see the total what is the coding function. First, the system initialization setup. Serial communication established at 115200 baud. And second, pin mode from configured PIR as input, pump as output. The third, safe low state on initialization to prevent premature watering. Automatic connection handling to local Wi-Fi gateway. And next will be the closed loop automation. First will be the execute deterministically with a 5-second update interval. Second, threshold mechanism. If analog soil moisture value bigger than 700, indicating dry soil condition, so the pump pin is driven high to irrigate. And third, once moisture is restored and falls below the threshold, the pump immediately turns off. Next. So here will be the cloud platform integration. First, IoT architecture. Lightweight HTTP REST API over standard network port 80. Cloud host connected directly to the centralized ThinkSpot.cloud server instance. And third, security and authentication. Managed via a unique embedded 20 character cryptographic device access token within the firmware authorization headers. Next, I'll pass to my friend.
So now I will present about the case study in the real world scenario. So for the Farm X in Johor have 250 meter square greenhouse with 5 rows of sensitive and high level strawberries. So right now, 3 workers monitors the plants 24 hours per 7 days. They water, check temperature and humidity every 3 hours and do night security. These manual methods cause the more problem. So for example, the worker often water too much or too little, which damage the strawberry roots. Rebel costs are higher, about 5,100 per month. So our IoT solutions use soil moisture sensors for automatic waterings, DHT sensors for continual climate control, and PIR sensors for night security. So this reduce the rebel cost and protect the plant better and increase the stability rate. So we use the temperature, humidity, and place it at the front, middle, and the back of the greenhouse. And the purpose is used to monitor the temperature and humidity distributions inside the greenhouse. And we used six soil moisture sensors and place at the both end of the left, middle, and the right vertical rack, which is the row 1, 3, and 5. The purpose is used to monitor soil moisture and activate the water pump when the moisture level fall below the specific threshold. So for the last is the motion sensors. We place at the main entrance and the rail exit. It used to detect the motion at the night and activate the alarm system if the animals or people enter the greenhouse. So next. So this is our total cost breakdown in our project. So the first one is not MCUs, which is 17 and 90 cents. And the next one is the temperature humidity is 4 ringgit and 10 cents. And next is soil moisture is 4 ringgit and 80 cents. And motion sensor is 4 ringgit and 90 cents. And the mini pump is 3 ringgit and 90 cents. And the PVC cable is 1 ringgit. And duct bonds we use male male to female, and female to female. So which is 3 ringgit and 50 cent, 2 ringgit and 79 cent, and 2 ringgit and 79 cent. And the breadboard is 2 ringgit and 90 cent. For our cloud platform subscriptions is 0 ringgit is because we use the free trial. So the total estimate cost in our project is around 50 ringgit. So next.
Okay, so for the conclusion, our project successfully achieved all its goals. We built a highly cost-effective system using the remote controller and ThingsBoard cloud. It successfully collected over 600 data samples for real-time monitoring and automated watering, proving that smart agriculture doesn't have to be expensive. The main contribution of this project is proving that the effective smart irrigation is possible without costly industrial equipment. We created a full hardware to software architecture using simple HTTP protocol, providing a practical reference and foundation for future IoT research. Every project has their limitation. So for our prototype, use low cost sensor which have a low precision, and we only test it indoor for 4 days on a single plant. Additionally, the system depends heavily on continuous Wi-Fi and uses simple threshold logic rather than smart decision making. So in future, we plan to upgrade to higher precision capacitive sensor and switch to MQTT protocol for better scalability. We also aim to add local SD card backups, use LoRa for large-scale multi-node setup, and introduce machine learning to predict weather and optimize water use. So that's all from our group. Thank you.